Imagine, for a second, trying to parallel park a skyscraper.
Right.
But you're attempting this in like a total vacuum, and you are driving directly into a blinding, unshielded solar glare.
Oh, yeah.
And on top of that, your thrusters are kicking up this supersonic sandstorm of microscopic glass razor blades.
Just an absolute nightmare scenario.
Right. And I mean, if your sensors fail for even a fraction of a second, or, if a shadow hides a 10-foot boulder, you don't just scratch the bumper.
No, you definitely don't.
You die. So welcome to the deep dive. Today, we are strapping in for, well, the absolute ultimate engineering thrill ride.
We really are. The scenarios we're looking at in today's source material, they really do redefine the entire concept of a hostile work environment.
Yeah, totally.
Because, we like to think of human engineering as this highly controlled, pristine discipline.
Sure, like building a bridge or something.
Exactly. You survey the bedrock, you calculate the wind shear, you select your steel, and, well, the blueprint holds. But space exploration, it just completely shatters that illusion.
Because the blueprint is constantly being vaporized by the environment itself. I mean, if you're listening to this, you likely already appreciate that, just getting a rocket off a launch pad and into Earth orbit is this agonizing feat of physics.
Oh, absolutely. It's incredibly hard.
But orbit is relatively clean, right? Orbit is just math and velocity.
It's predictable.
Yeah, predictable. But dropping down out of that orbit, plunging through atmospheric fire, or like falling through toxic acid clouds, or descending into razor-sharp vacuum dust just to set your robotic skids or human boots on a foreign surface. Well, that is where the science truly gets wild.
Yeah, the transition from orbit to surface is without a doubt the most vulnerable phase of any mission.
It has to be.
And each destination we are breaking down today represents a completely distinct, uniquely lethal puzzle. The engineers aren't just building vehicles here.
No, they're basically inventing new science.
Right. They are forced to invent entirely new fields of applied physics, just to ensure the hardware survives the exact moment of touchdown.
And that's wild.
I mean, a lander perfectly designed to survive one of these worlds would be instantly annihilated by any of the others.
Instantly. Which brings us to the mission for today's deep dive. If you think you know what space travel looks like, prepare to have those assumptions fundamentally challenged.
Prepare to be surprised, yeah.
We are exploring 5 upcoming NASA landing missions. And these are targeting planets and moons all across the solar system, mostly slated for the late 2020s and 2030s.
It's a very busy upcoming decade.
Oh, hugely busy. We're going to break down exactly what these probes and crewed landers will physically experience during their descents and, uncover the massive scientific mysteries they are being set to solve.
But the science is just as crazy as the engineering.
Looking through our sources, the physical extremes involved are just staggering.
The sheer diversity of the hostility is what really stands out to me. The solar system is not a monolith,
No, not at all.
It's this collection of extreme laboratories. And to understand them, we basically have to meet them on their own terms.
So let's meet the first one. We are heading nearly 1 billion miles away from Earth.
A long trip.
Yeah, out to a world that completely flips our understanding of what an atmosphere even is. We are heading out to Saturn's massive moon, Titan.
Titan is an absolute jewel in planetary science. I mean, for astrobiologists, it is arguably the most compelling target we have ever identified.
Wow, so the mission architecture here puts a target launch around, I think, 2028?
Roughly 2028.
With an arrival out at Saturn around 2034.
Right, so it's a long, cold coast through deep space.
But the payload waiting at the end of that journey is what absolutely blows my mind. The mission is called Dragonfly.
Dragonfly, yes! Such a cool concept.
It really is. Because we aren't sending a stationary lander that just sits there taking photos of the same rock for 10 years.
No.
And we aren't even sending a wheeled rover crawling at like half mile an hour. Dragonfly is an 8-rotor, nuclear-powered coaxial octocopter.
Which is just an incredible sentence to say out loud.
I know, right? To put a visual on this for you, picture a nuclear-powered drone the size of a ride-on lawnmower.
Yeah, the visual is stunning, but the engineering that actually makes it possible is even better.
Okay, let's unpack this, because how does that even work?
Well, the reason we can fly a multi-rotor drone 1 billion miles away, it comes down to Titan's bizarre atmospheric physics.
Okay.
It is the only moon in our entire solar system with a dense atmosphere.
Right, our moon has basically nothing.
Exactly. Ours is a vacuum. But Titan's isn't just dense. It is this heavy nitrogen atmosphere that is roughly 4 times denser than the air we are breathing right now on Earth.
4 times, so the air is physically thick.
Very thick. And incredibly cold. The ambient surface temperature sits around minus 290 degrees Fahrenheit.
Oh man, minus 290.
Yeah, it's brutal. But the crucial variable here, the one that makes Dragonfly work, is the gravity. Titan's gravity is only about 1/7 of Earth's.
1/7. So I was looking at that combination in the notes. High atmospheric density paired with incredibly low gravity, and the implications are wild.
They really are.
I mean, if you were standing on the surface of Titan, wearing a heavily insulated spacesuit, obviously.
Obviously, or you'd freeze solid.
Right. But if you just strapped a pair of cardboard wings to your arms and flapped, you could literally achieve lift.
You really could.
You could fly with human muscle power alone. That is insane.
The aerodynamics completely shift in that environment. For context, if you think about flying a helicopter on Mars, which NASA did with Ingenuity, right?
It's a little Mars helicopter.
Right. Doing that requires massive ultralight blades spinning at furious speeds because the Martian atmosphere is only about 1% as dense as Earth's.
So you're practically trying to fly in a vacuum on Mars.
Exactly. But on Titan, the dense air provides a massive amount of aerodynamic bite for the rotors. And the low gravity means the vehicle weighs a fraction of what it would here on Earth.
So a heavy nuclear-powered drone can lift off with relative ease.
Precisely. It's the perfect place to fly.
I want to break down that phrase I used earlier, coaxial octocopter, because it speaks to the mechanical reality of flying in an alien sky. Coaxial means the rotors are stacked on top of each other, right?
Yes. So you have 4 arms extending from the main body, and at the end of each arm, there are 2 rotors stacked vertically.
Okay.
And they spin in opposite directions.
Not opposite directions.
It's all about canceling out torque. If all the blades spun the same way, the body of the drone would just violently spin in the reverse direction.
Oh, like a top.
Right. By having the stacked rotors spin opposite to one another, those rotational forces cancel out, keeping the vehicle perfectly stable.
That makes sense.
And having 8 rotors provides critical redundancy.
So if one breaks.
Exactly. If one motor fails in the freezing methane air, the flight computer can instantly adjust the power to the other 7 to maintain a controlled hover.
That is so smart. But before Dragonfly can even attempt to hover, it has to survive the arrival.
And that is the terrifying part.
Right, because hitting an atmosphere 4 times denser than Earth's at interplanetary speeds, that seems like hitting a brick wall.
The entry phase is incredibly brutal. When the Dragonfly entry capsule arrives, it hits that thick nitrogen atmosphere at hypersonic speeds.
Wow.
And atmospheric drag acts as a massive aggressive brake. The physics here are intense. The spacecraft is moving so fast that it violently compresses the nitrogen gas directly in front of it.
So it's not even friction, really. It's compression.
Exactly.
Yeah.
That rapid compression generates phenomenal heat. We're talking about a glowing plasma sheath enveloping the entire capsule.
So it requires a heavily engineered heat shield just to absorb the punishment of that compression heating.
It absolutely does. And then as it bleeds off that extreme velocity, it deploys drogue parachutes.
Just to stabilize it.
Right. And then the main parachutes deploy, slowing its descent down through the hazy orange alien sky.
But the critical transition, the moment that makes or breaks, like a decade of planning, happens while it is still falling.
It's a nail-biter.
Because the aeroshell opens up and Dragonfly just drops free. It is literally in free fall through an alien sky.
With no human pilot.
Right. There is no joystick control from Houston because the light delay to Saturn is over an hour.
So they can't do anything but watch.
It has to independently fire up its 8 rotors, stabilize its attitude, identify its landing zone using onboard sensors, and touch down softly, completely on its own power.
The autonomous navigation required for that sequence is just a massive leap forward in spacecraft design.
I can't even imagine the coding involved.
It's staggering. It has to visually track the terrain below it in real time, matching what it sees with its preloaded maps of the Shangri-La dune fields.
Shangri-La. It sounds tropical, but we are talking about vast equatorial regions covered in massive linear dunes.
Right, but these aren't sand dunes like you'd find in the Sahara.
No, they're not. The sand isn't made of silica or crushed rock. It's made of organic material.
Which is mind-blowing.
It really is. And this brings us to the core science of the mission. Why is Titan the ultimate dream destination for astrobiologists?
What's fascinating here is that Titan acts as a planetary-scale time machine.
A time machine.
Yeah, it is widely considered to be a prebiotic chemistry analog for early Earth.
Okay, prebiotic meaning.
Meaning it gives us a snapshot of the complex chemistry that might have existed on our own planet right before biological life took hold.
So the chemical building blocks are there, but they haven't quite organized into living cells yet.
Exactly the concept.
Yeah.
You see, on Earth, we have a hydrological cycle driven by water.
Right, rain, rivers, oceans.
But on Titan, water is frozen so hard it acts as the bedrock.
Yeah.
It is literally the rock of the moon.
That is so weird to think about. Water as bedrock.
It's bizarre. Instead of water, Titan has a methanological cycle.
What methanological cycle?
Yeah, you have liquid bodies, huge lakes and rivers made of liquid methane and ethane just sitting there at minus 290 degrees.
And the organic sand, where does that come from?
It actually starts high up in the atmosphere. Solar ultraviolet radiation and particles from Saturn's magnetic field strike the methane and nitrogen molecules high in Titan's sky. This high energy breaks the chemical bonds of those simple gases, which allows them to recombine into much larger, complex organic polymers.
Like plastic.
Sort of similar chemically, yeah. Planetary scientists call these molecules tholins.
Tholins.
Right. And over time, these heavy, complex organics literally rain down from the sky. They coat the icy surface in this dark, organic sludge.
So it is literally raining the fundamental building blocks of life.
Exactly.
And over millennia, the winds of Titan whip this organic material into massive, towering dunes. So Dragonfly lands in this freezing organic sandbox.
And it comes prepared. On its landing skids, it actually has rotary drills.
Oh, that's awesome.
The sampling mechanism is ingenious. It uses those drills to break up the frozen organic sand. Then a pneumatic system essentially vacuums that material up into the body of the drone.
Like a literal vacuum cleaner.
Basically, yeah. And it feeds it into an onboard mass spectrometer.
Okay, let's explain how that works, because we throw the term mass spectrometer around a lot in space science.
We do. It's a staple.
How does a machine actually figure out what a grain of alien sand is made of?
Well, a mass spectrometer essentially acts as an incredibly precise molecular scale.
Okay, a scale.
Right. So once the sample is inside, the machine vaporizes it, turning the solid material into a gas.
Turning sand into gas.
Yes. Then it hits that gas with an electron beam. And this beam knocks electrons right off the molecules, giving them a positive electrical charge.
So it ionizes them.
Yes, exactly. Once they are charged, they get shot down a curved tube surrounded by a powerful magnetic field.
Okay, I'm picturing it.
And because they have a charge, the magnetic field bends their path. The lighter molecules take a very sharp turn.
Because they're lighter, so they get yanked easier.
Exactly. While the heavier, more massive molecules take a wider, slower turn.
Right.
So by measuring exactly where the molecules hit a detector at the end of that curve, scientists can determine the precise atomic weight of every single component in that sand.
Oh, wow. So it's physically sorting the chemical recipe by weight.
It is. It tells us exactly which elements, carbon, hydrogen, nitrogen, oxygen are present, and in what exact ratios.
And they are looking for something specific, aren't they? Amino acids. The actual raw recipe for life.
Finding amino acids or complex lipids, there would be a monumental discovery. It would change everything.
It really would.
And to increase their chances, Dragonfly isn't just staying in the dunes. Its ultimate destination, after a series of long autonomous flights, is a specific region called Selk Crater.
Selk Crater, that's an ancient meteor impact site, right?
It is, and the physics of an impact on a world like Titan create a very specific temporary environment.
Temporary how?
Well, when a massive meteor strikes Titan's frozen water ice bedrock, the kinetic energy of that impact is converted into immense heat.
Okay.
That heat violently melts the ice.
So for a brief period in Titan's geological history, Selk Crater wasn't just a dent in the ice. It was a massive churning pool of liquid water.
Yes. And that liquid water immediately mixed with the thick layer of complex organic tholins that had been raining down from the sky.
Oh, wow. You have liquid water, which is the universal solvent, mixing with complex organic molecules, all powered by the residual thermal energy of a meteor impact.
It is basically a temporary cosmic crockpot with all the ingredients for life.
A cosmic crockpot. I love that.
But, the clock is always ticking on that crockpot.
Because it's minus 290 degrees outside.
Exactly. Eventually, the heat dissipates into the freezing environment, and the crater freezes solid once again.
Right.
But in doing so, it traps whatever chemical reactions occurred right there in the ice. By flying to Cell Crater and drilling into that specific ice, Dragonfly might uncover chemical pathways frozen in time.
The exact intermediate steps that bridge the gap between dead chemistry and biological life.
Exactly.
We are sending a nuclear drone to surf a freezing orange sky to find out how life begins. The elegance of that mission is astonishing.
That's poetry, honestly.
But Titan is just one extreme. While Titan offers a thick atmosphere where we can fly and hunt for organics, what happens when atmospheric density is dialed up so high that it becomes an active, crushing weapon?
Oh boy, you transition from a freezing prebiotic laboratory to an absolute planetary nightmare.
Right, you get Venus.
Venus.
We're moving from the outer solar system back into the inner solar system.
Light.
Venus. Specifically, a mission called DAVINCI.
Right, which stands for Deep Atmosphere Venus Investigation of Novel Gases, Chemistry, and Imaging.
That is a mouthful. Also targeting a launch and arrival in the late 2020s or early 2030s.
It is. Venus is frequently referred to as Earth's twin, mostly because it is similar in size, mass, and composition.
But it's an evil twin.
It is a twin that has gone terrifyingly wrong. It is the solar system's premier cautionary tale of a runaway greenhouse effect.
Yeah.
And people often forget that NASA hasn't sent a dedicated atmospheric descent probe down through Venus's lower atmosphere in decades.
Really? Why not?
The environment is so intensely hostile that it has been heavily neglected in favor of Mars. Mars is just so much easier to survive.
That makes sense. So the payload for DAVINCI is a spherical titanium descent probe released from a main carrier spacecraft.
A very heavily armored sphere.
Right. We just talked about the aggressive, hypersonic braking Dragonfly experiences at Titan. The descent into Venus takes that aggression to a whole different level, because DAVINCI is plunging into the Venusian cloud tops at over 25,000 miles per hour.
25,000 miles per hour. The kinetic energy involved in entering the atmosphere at that speed is immense.
I can't even fathom it.
The heat shield will endure temperatures that would instantly vaporize most metals.
Just on entry.
Just on entry. And the environment it is plunging into is chemically antagonistic. The upper cloud layers of Venus aren't made of benign water vapor, like on Earth.
No.
They are primarily composed of concentrated sulfuric acid.
So you punch through a literal acid bath at orbital velocity.
Exactly.
But the acid is just the greeting. The probe sheds its heat shield, deploys its parachutes, and begins a roughly 60-minute glide down through the atmosphere.
Right.
And over that single hour, the conditions worsen by the second. By the time it approaches the surface, the atmospheric pressure is 92 times greater than Earth's at sea level.
92 times. It's a concept called hydrostatic pressure.
Okay.
The sheer weight of the 60-mile-thick column of heavy carbon dioxide gas pressing down on the surface is relentless.
To put that 92 times pressure into perspective for you, standing on the surface of Venus feels identical to being 3,000 feet underwater here on Earth.
Right.
The physical crush is unimaginable. It would flatten a conventional submarine.
It really would. Which dictates the fundamental engineering of the probe. It has to be a sealed titanium sphere.
Because of the shape.
Yes. A sphere is the optimal geometric shape for distributing external pressure evenly across its surface. It prevents any single point from buckling.
Oh, okay.
It is built like a deep-sea bathysphere, basically. But instead of water, it is swimming through supercritical carbon dioxide.
Supercritical meaning the pressure is so high, the gas starts behaving almost like a liquid.
Exactly. It's a bizarre phase of matter.
And paired with that crushing pressure is furnace-level heat. The surface temperature is around 900 degrees Fahrenheit.
900 degrees.
That is hot enough to melt lead. It is hot enough to cook conventional silicon electronics into useless slag in minutes.
Yeah, standard electronics don't stand a chance. The thermal management system inside that titanium sphere has to fight a losing battle for an hour.
How does it even do that?
It utilizes phase change materials, essentially specialized waxes that absorb heat as they melt.
Oh, clever.
Right, it uses that melting process just to keep the delicate scientific instruments inside at operational temperatures for a few more minutes.
Just buying time. Literally buying minutes.
So the target landing site is a rugged, mountainous region called the Alpha Regio Tessera Highlands. But here's where I have to step back and analyze the friction in this mission profile.
Okay, go ahead.
Because DAVINCI is designed primarily as a descent probe. It takes its measurements on the way down.
Correct.
If it actually manages to survive the physical impact with the jagged ground, which isn't guaranteed, it is only projected to transmit data for a mere 17 to 20 minutes.
Right, before the internal temperature spikes. Before it spikes, the electronics fail, and the titanium yields to the crush. So what does this all mean? From a purely logistical standpoint, how does a scientist justify spending hundreds of millions of dollars and a decade of engineering on a spacecraft that the math guarantees will die in 20 minutes?
It's a tough sell.
What is the actual return on investment?
This raises an important question, but it is the ultimate high-stakes gamble. The justification hinges entirely on the data it collects during that 60-minute fall.
Okay.
And specifically, it's about solving the mystery of Venus's deep past. The primary scientific goal of DAVINCI is to ingest the atmosphere as it falls and measure noble gases.
Noble gases like xenon, krypton, and argon.
Exactly, along with specific atmospheric isotopes.
Okay, I am stuck on something here.
Sure.
If Venus is a 900-degree high-pressure chemical blender where sulfuric acid and supercritical CO2 are constantly interacting, how can any gas survive that environment long enough to tell us what happened a billion years ago? Why are noble gases the key here?
It all comes down to atomic structure. Noble gases have a completely full outer shell of valence electrons.
Okay, going back to high school chemistry.
Right. In chemistry, atoms react and bond with each other by sharing or stealing electrons to fill their outer shells. But because noble gases are already full, they are perfectly content.
They don't need anyone else.
Exactly. They are inert. They absolutely refuse to react with other elements.
So they don't get locked up in the rocks.
Yep.
They don't participate in the acid rain cycle. They just float there.
Precisely. They act as a permanent, untampered ledger of the planet's entire history.
Wow.
By measuring the exact ratios of these noble gases and specific isotopes, scientists can actually reverse engineer the planetary timeline.
That's incredible.
For example, one of the most critical measurements DAVINCI will take is the ratio of regular hydrogen to deuterium.
Deuterium. That's a heavier isotope of hydrogen, right?
Yes.
How does that ratio prove anything about the past?
Well, if Venus once had vast liquid water oceans, like Earth does, it would have had a lot of hydrogen. Water is H2O, after all. Right. As the runaway greenhouse effect took hold and those oceans boiled into vapor, solar radiation bombarded that water vapor high in the atmosphere.
Splitting it apart.
Exactly, splitting the oxygen from the hydrogen. Now, normal hydrogen is very light, so it easily escaped Venus's gravity and bled out into space.
Okay.
But deuterium, being heavier, was left behind.
Oh, so if DAVINCI sniffs the atmosphere and finds an abnormally high concentration of deuterium compared to regular hydrogen,
And it proves that Venus used to have massive amounts of water that boiled away.
the isotopic ratio is literally the smoking gun for lost oceans.
It is. Those 60 minutes of data collection can definitively answer whether Venus was once a second blue marble in our solar system with a climate that could have supported life before the catastrophe.
That is profound.
It really is.
And then there is the final desperate phase of the descent. As DAVINCI breaks beneath the thick, opaque cloud layers and finally gets a clear view of the surface, it is going to use a specialized camera to snap hundreds of high-resolution infrared photos of the ground as it rushes upward.
Yes, and it has to use specific infrared wavelengths because the deep atmosphere of Venus absorbs a lot of visible light. It's very dark down there.
Right.
So the camera looks through these windows in the infrared spectrum where the atmosphere is transparent, and it is aiming at the tesserae in the Alpha Regio.
These tesserae are crumpled, highly deformed mountainous landforms,
Mm-hmm.
and we've only ever seen them via low-resolution radar from orbit.
Right, through the clouds, and the geologic community is doubly suspicious of the tesserae.
Suspicious how?
While on Earth, our continental crust is made of granite, and granite requires liquid water and plate tectonics to form.
Got it.
If the infrared images reveal that the tesserae are made of granitic rock, it would heavily imply that Venus not only had oceans, but also active plate tectonics.
It would mean Venus had continents.
Exactly, continents.
So those 17 to 20 minutes on the surface, transmitting those high-res images back up to the relay satellite before the titanium cracks and the electronics fry. That might provide our only visual window into a lost epoch of planetary evolution.
It's essentially a suicide mission, yes. But the data fundamentally rewrites the history of the solar system.
It forces us to realize that planetary habitability isn't a permanent state.
No, it is a delicate balance that can be lost.
That's terrifying. Now, Venus proves that a thick atmosphere can be an active weapon that will crush you.
Definitely.
So the logical engineering solution, if you want a spacecraft or a human crew to survive, might seem to be going somewhere with zero atmosphere, right?
It seems intuitive.
Remove the crushing pressure, remove the aerodynamic heating. But as NASA is finding out with the Artemis program, Stripping away the atmosphere doesn't make things safer.
No, it really doesn't.
It just trades the hydrostatic pressure for razor-sharp vacuum physics. We are shifting our focus to the lunar South Pole.
The Artemis III mission, the highly anticipated return of humanity to the lunar surface.
Targeting the late 2020s, NASA is utilizing a commercial human landing system, or HLS vehicles like the massive SpaceX Starship HLS or the Blue Origin Blue Moon to carry astronauts to a completely unvisited region of the moon. Now, the Apollo missions landed on the moon in the 1960s and 70s. We've been there. But the South Pole is an entirely different operational environment.
The contrast is stark, completely different. The Apollo missions specifically targeted the equatorial regions of the moon.
The flat parts.
Yes. Those areas are dominated by the lunar Maria, relatively flat, smooth, basaltic plains that are well lit by a high sun.
Which you need when you're flying with 1960s computers.
Exactly. With the rudimentary computing power of the Apollo guidance computers, flat and well lit was a strict requirement for survival. The lunar South Pole, however, is a treacherous, highly jagged landscape of stark mountain peaks and incredibly deep, ancient craters.
The topography is brutal. But the lighting conditions are what make it truly terrifying.
The lighting is the hardest part.
Because it is the pole, the sun never passes overhead. It sits perpetually right on the horizon.
Like permanent twilight.
Right. So the lander is coming down through a high-contrast nightmare. You have blinding, unshielded solar glare reflecting horizontally off the high crater ridges, sitting directly adjacent to deep abysses of eternal, pitch-black darkness.
There's no atmospheric scattering to soften the shadows.
Here's where it gets really interesting, because I think of this descent as trying to parallel park a skyscraper while driving directly into a blinding sunset.
That's a great way to picture it.
And to make matters worse, you are kicking up a sandstorm of razor blades as you do it.
Ah, yes. That sandstorm of razor blades is formally known in aerospace engineering as plume surface interaction, or PSI.
PSI.
And it is arguably the single most critical engineering hurdle of the Artemis descent.
Let's dive deep into the mechanism of PSI. Because a rocket engine, firing in a vacuum, behaves entirely differently than it does on a launch pad here on Earth.
Radically different. On Earth, when a rocket fires, the thick atmospheric pressure of our air pushes back against the exhaust plume.
It kind of holds it in.
Right. It constrains the hot gases, keeping them relatively column-shaped and localized under the rocket. In the vacuum of space, however, there is absolutely zero atmospheric pressure to hold that plume together.
The gas just expands infinitely outward.
Instantly. The moment the high-pressure exhaust leaves the engine nozzle, it violently expands horizontally. It moves parallel to the lunar surface at immense supersonic speeds.
And it interacts directly with the lunar regolith.
It does.
Regolith being the lunar dirt. But we have to clarify how that dirt was made, because it is nothing like Earth dirt.
No, not at all.
On Earth, a grain of sand is created by wind and water rolling rocks together over millions of years, smoothing their edges until they are round.
The moon has no wind, no water, and no weather. The regolith was created by billions of years of micrometeoroids slamming into the lunar bedrock at tens of thousands of miles per hour.
Just constant bombardment.
Constant. And each impact acts like a microscopic bomb, shattering the rock and instantly melting it into tiny glass shards that cool instantly in the vacuum.
So lunar dust is essentially microscopic, unweathered, jagged glass.
Yes. It's incredibly abrasive.
We actually have a historical precedent for how destructive this is. During Apollo 12, the lunar module intentionally landed about 500 feet away from an old robotic probe called Surveyor 3.
Oh, I remember this.
Yeah. When the astronauts walked over to inspect Surveyor 3, they found that the exhaust plume from their landing had accelerated the lunar dust so violently that it literally sandblasted the paint off the robotic probe from hundreds of feet away.
And keep in mind, the Artemis landers, like Starship, are vastly more powerful than the Apollo module.
Vastly more powerful.
The thrust requirements are orders of magnitude higher. As the HLS descends, those giant engines will blast massive quantities of this high-velocity, glass-sharp regolith outward.
It creates an obscuring, highly abrasive sheet of material.
Moving at supersonic speeds, scouring the landing site, and severely degrading the astronauts' ability to visually gauge their altitude and lateral drift.
Which means looking out the window during the final, most critical seconds of touchdown is virtually useless.
You can't see a thing.
The crew and the vehicle computers will be relying entirely on autonomous hazard avoidance sensors.
They rely heavily on LiDAR light detection and ranging.
Okay, how does that help them see through the dust?
Well, it fires rapid laser pulses at the ground and measures how long it takes the light to bounce back. This creates a real-time, high-resolution 3D topographical map of the surface below.
So the computer has to punch through the dust, scan the blinding light and the deep shadows, and instantly process that data to find a flat spot free of massive boulders or extreme slopes.
All in real time while descending.
And if they manage to thread that needle and touch down safely, the environmental hostility doesn't end. They step out of the vehicle and have to confront the severe thermal realities of the South Pole.
The thermal gradients are mind-boggling.
How bad is it?
Well, in the areas illuminated by that horizontal sunlight, the surface temperature can reach positive 250 degrees Fahrenheit.
Boiling hot.
Right. But right next to those sunlit peaks are the permanently shadowed regions, or PSRs.
Because the moon's axis is barely tilted compared to Earth's, so the sunlight comes in completely horizontally. It never shines down to the bottoms of these deep polar craters.
Exactly. Those crater floors haven't seen a single photon of direct sunlight in billions of years.
Billions.
So when the astronauts step out of the glare and into those shadows, the temperature instantly plunges to minus 330 degrees Fahrenheit.
Oh my God.
That is colder than the surface of Pluto.
Just a few feet away from 250 degrees.
Yes. The materials engineering required for the spacesuit joints just to survive the transition from extreme heat to cryogenic cold without cracking or seizing up, it's a monumental achievement.
Which naturally leads to the ultimate question. If this location is a jagged, blinding, cryogenic nightmare, why are we risking human lives to go there? Why not just go back to the safe, flat equator?
If we connect this to the bigger picture, the answer is water.
Water.
Those terrifying, permanently shadowed regions are the entire strategic point of the Artemis program. They act as thermal cold traps.
Okay, meaning what exactly?
Okay. Well, over the last few billion years, whenever a water-rich comet impacted the moon, the heat of the impact vaporized the comet's water.
Right.
That water vapor drifted around the exosphere until it happened to drift into one of these deep freezing polar craters.
Oh, I see. And once it hits minus 330 degrees, it immediately freezes solid.
Instantly. And it can never sublimate back into a gas because the sun never hits it. It is trapped forever.
So over millions of years, that water ice has steadily accumulated.
Exactly. The Artemis III astronauts are tasked with navigating into these shadows to prospect and extract samples of that ancient ice.
Because if you have abundant ice water on the moon, you have secured the holy grail of deep space exploration.
It changes the entire paradigm.
Let's break down the mechanics of why water is the holy grail.
Yeah.
It isn't just about astronauts having something to drink, although that is important.
It is about propulsion. Water is H2O, using a relatively simple process called electrolysis. Basically running an electrical current generated by solar panels through the melted water, you can break the chemical bonds.
You separate the hydrogen gas from the oxygen gas.
Yes. You can use the oxygen to fill the life support systems for the crew to breathe, but more importantly, you can chill both gases down until they liquefy, storing them in cryogenic tanks.
Liquid hydrogen and liquid oxygen. That is literally high-efficiency rocket fuel.
You have just built a gas station on the moon.
Wow.
If we can reliably harvest and refine that ice, future missions to Mars or the outer solar system won't have to carry millions of pounds of heavy fuel up through Earth's deep gravity well.
Which is incredibly expensive.
Exactly. They can launch from Earthlight, stop at the moon, fuel up using lunar resources, and blast off into deep space. The lunar South Pole is the strategic gateway to the rest of the cosmos.
The logic is unassailable. Now, with the moon, we have humans in the loop. Humans are adaptable. If a sensor fails or a boulder suddenly appears through the dust, a human pilot can take over, adapt to the complex terrain, and make a split-second decision to alter the flight path.
Right. Humans are the best computers for that.
But how do we achieve that level of complex, multi-stage operation on a world that is millions of miles away? The light delay makes remote control impossible, and the environment is too distant for humans right now.
We have to rely on the ultimate automation. We shift our focus to Mars, and specifically the Mars Sample Retrieval Lander.
The robotic relay race of Mars. Targeting the late 2020s or early 2030s, this mission architecture is heading to Jezero Crater. Right now, NASA's Perseverance rover is already there.
It's been busy.
Right. It is driving around the dry, ancient river delta of Jezero Crater, using its robotic arm to drill core samples of ancient rock, sealing them in pristine titanium tubes and systematically dropping them on the Martian surface like breadcrumbs.
Perseverance is just the collection phase of a multi-decade campaign. But Percy was never designed with the capability to bring those tubes back to Earth.
It's just a hoarder.
Exactly. That is the job of the Sample Retrieval Lander, or SRL.
The payload here is staggering. It is the heaviest robotic lander ever designed for Mars. And strapped to its deck is something completely unprecedented in spaceflight history.
The Mars Ascent Vehicle, or MAV.
A fully fueled, multi-stage rocket waiting to be launched from another planet.
The physics of landing a payload of this mass on Mars presents a very unique conundrum. The Martian atmosphere is incredibly frustrating for aerospace engineers.
Why is it frustrating?
It is the worst of both worlds. The atmosphere is dense enough, about 1% of Earth's, that a spacecraft arriving at interplanetary speeds will generate intense frictional heating.
So you absolutely require a robust heat shield.
You do, but the atmosphere is far too thin to generate enough aerodynamic drag to slow a heavy payload down to a safe landing speed using parachutes alone.
Oh, I see.
If you just use parachutes, you will still hit the ground at hundreds of miles an hour.
Hence the infamous 7 minutes of terror. The entry capsule hits the thin Martian air. The heat shield glows white-hot as it bleeds off the initial velocity. It deploys a massive supersonic parachute to slow down further, and then it has to perform a highly complex mechanical divorce.
The sky crane maneuver.
Right. The parachute and back shell drop away, and the lander falls freely. It ignites its retro rockets to perform an autonomous maneuver called the sky crane redux.
Because the vehicle has to actively fly itself horizontally, scanning the terrain below with its own radar and LiDAR, avoiding the craters and boulders of Jezero until it finds a flat landing zone perfectly positioned near where Perseverance left its sample cache.
It's doing all of this on its own.
Completely autonomous. It hovers, lowers the heavy lander down on a tether, and once the wheels touch, the descent stage cuts the cords and flies away to crash at a safe distance.
Okay. Assuming the heavy lander survives the sky crane maneuver, the robotic transfer phase begins. This is where the relay race happens.
The most complex part.
The lander deploys a specialized robotic arm. Meanwhile, Perseverance drives over and begins handing the titanium tubes to the lander. Or, as a backup plan, the lander might deploy a fleet of specialized mini-helicopters, descends the Ingenuity drone to fly out, scoop up the tubes, and fly them back to the lander.
The backup plan is almost as crazy as the main plan.
It is. And then the lander's arm takes these tubes and loads them securely into the payload bay of the Mars Ascent Vehicle.
And this leads to the absolute climax of the entire architecture. The MAV is going to ignite its engines directly on the dusty surface of Mars.
Let's talk about the propulsion of the MAV, because they aren't using the liquid hydrogen and oxygen we just discussed for the moon.
No, they can't.
The MAV uses a solid rocket motor. Why solid fuel?
Reliability and environmental stability.
Quote.
Liquid fuels require complex plumbing, turbopumps, and precise thermal control. If liquid fuel gets too cold, it freezes. If it gets too hot, it boils off and vents away.
And Mars is not exactly climate controlled.
Exactly. The MAV has to sit on the freezing surface of Mars for months, experiencing wild temperature swings while the robotic transfer happens. A solid rocket motor is essentially a highly engineered, controlled explosive.
Right.
It is physically stable, requires no complex plumbing, and is virtually guaranteed to ignite when the electrical command is sent.
It is a massive Roman candle. When the command is given, the MAV ignites, kicking up a storm of red dust, and becomes the first rocket in history to launch off the surface of another planet.
It climbs out of the Martian gravity well and inserts the sample container into low Mars orbit.
But the journey isn't over.
Not even close.
A separate orbiter, provided by the European Space Agency, which has been waiting patiently in Mars orbit, has to perform an automated rendezvous.
It has to track down this basketball-sized sample container hurtling through orbit.
It captures it, seals it in an Earth entry capsule, ignites its own engines, and ferries the payload all the way back across the solar system, eventually dropping it into the Utah desert.
The ambition is magnificent.
The visual of the MAV blasting into the pink Martian sky will be a defining image of our century. But I have to play the skeptic here.
Okay, let's hear it.
I am looking at the sheer logistical friction of this outline. A rover collects dirt and drops it. A heavy lander flies from Earth, performs a terrifying sky crane landing. A robotic arm and helicopters play fetch with the dirt. They load it into a solid rocket. The rocket launches into orbit. A European orbiter plays catch with it in space and then flies millions of miles home.
It's a lot of steps.
The risk of total failure at any single one of those transfer points is incredibly high. So is this hyper-complex Rube Goldberg architecture truly necessary just to get a few tubes of dirt?
It's a fair question.
I mean, we have incredible laboratories miniaturized on our rovers right now.
Yeah.
Curiosity and Perseverance have chemical analyzers. Why can't we just study the dirt with the robots we already have on site?
It is the most common and valid critique of the Mars sample return mission. The cost and complexity are astronomical.
Right.
But the answer lies in the fundamental limitations of miniaturization and the burden of proof.
The burden of proof for what?
For discovering alien life. The core goal of collecting these specific rocks from an ancient river delta is to find unambiguous, undeniable signs of fossilized ancient microbial life.
Undeniable.
If NASA and ESA step up to a podium and announce to humanity that we are not alone in the universe, that life arose independently on another planet, the evidence cannot be ambiguous. It cannot be a statistical probability or a maybe.
It has to be airtight. It has to withstand the scrutiny of every skeptical scientist on Earth.
Exactly. And while our rovers are marvels of engineering, there are hard physical limits to what you can shrink.
Sure.
You simply cannot take a multi-ton, building-sized synchrotron particle accelerator or a massive transmission electron microscope requiring heavy electromagnets and high-vacuum chambers and bolt it to the chassis of a rover on Mars.
It is physically impossible.
Oh, the rovers can tell us the rock has organic carbon, but they can't tell us if that carbon was arranged into a cell wall.
I see.
To definitively prove the existence of ancient biological structures or chemical biosignatures, scientists need to slice these rocks at the nanometer scale.
Which you need Earth lens for.
Exactly. They need to subject them to chemical processes and imaging technologies that require the infrastructure of full-scale, state-of-the-art Earth laboratories. The terrifying complexity of the sample return mission isn't a design flaw. It is the unavoidable logistical price of definitive, unquestionable proof.
If you want the ultimate prize, you have to pay the ultimate price. That makes perfect sense. Now, the Mars mission represents the absolute pinnacle of massive, multi-billion-dollar, government-led space architecture.
It is an international coalition working for decades.
But as we move to our fifth and final mission, there's an entirely new paradigm emerging in planetary exploration.
The commercial era of spaceflight.
We're talking about treating space less like a massive one-off Apollo-style event and more like a commercial shipping route, utilized to solve highly localized, deeply bizarre planetary mysteries.
It's a big shift.
This is the CLPS program Commercial Lunar Payload Services. Instead of NASA building the lander, NASA's acting like a customer, buying payload space on private, commercially built lunar landers.
It fundamentally shifts the economics and the cadence of space access. By lowering the financial barrier to entry, it allows scientists to target very specific, very strange scientific anomalies that wouldn't necessarily justify a flagship multi-billion-dollar mission.
And the anomaly we are targeting today is the Lunar Vertex mission, heading to a location on the moon called Reiner Gamma.
Reiner Gamma is fascinating.
Let's paint a visual picture of this for you. If you look at the moon through a good telescope, you can actually see Reiner Gamma. It looks like a bright, swirling white tattoo painted directly onto the dark, flat basaltic plains of the lunar surface.
Planetary geologists call it a lunar swirl.
The lunar swirl.
And lunar swirls are one of the most aesthetically beautiful yet scientifically frustrating mysteries on the lunar surface.
The payload for Lunar Vertex is a commercial robotic lander equipped with a suite of instruments and a small micro rover. And what they are going to physically experience when they touch down at Reiner Gamma is profoundly weird.
Very weird.
To understand why, we have to talk about planetary magnetism. The moon, as a whole body, does not have a global magnetic field like Earth does.
Earth's magnetic field is generated by a churning liquid iron core. It acts as a massive deflector shield protecting our atmosphere and our biology from the constant barrage of lethal solar radiation.
And it makes our compasses work.
Right. Our compass needles point north because they align with this global field. The moon's core, however, cooled and solidified billions of years ago. The lunar dynamo is dead. It has no global magnetic field.
But Reiner Gamma is the glaring exception. It sits right on top of a highly localized crustal magnetic anomaly.
It is essentially an invisible, localized magnetic bubble trapped right in the crust of a dead moon.
It's like stepping into a localized force field. When the Lunar Vertex lander and its rover touch down inside this magnetic bubble, they're going to encounter surface dynamics that simply do not exist anywhere else on the Moon.
It's a unique environment.
Because of this localized magnetic field interacting with the raw vacuum of space and solar radiation, the local electrostatic environment goes crazy. The lander will literally experience levitating lunar dust.
The physics of electrostatic levitation are fascinating. It relies on the photoelectric effect.
The very concept Albert Einstein won his Nobel Prize for.
Exactly.
Walk us through how the photoelectric effect makes dirt float.
The lunar surface is constantly bombarded by high-energy ultraviolet photons from the sun. When these intense UV photons strike the microscopic shards of lunar dust, they pack enough energy to physically knock electrons right off the dust grains.
Okay, electrons carry a negative charge, so if the dust loses electrons, it becomes positively charged.
Yes, and because the ground beneath the dust is also being bombarded and losing electrons, the surface and the dust grains end up with the exact same positive electrical charge.
And just like pushing two positive magnets together, they violently repel each other.
The similarly charged dust grains repel the ground, causing them to physically lift off the surface and float in complex electrostatic fields. They get trapped within the invisible architecture of the local magnetic bubble.
The invisible forces of magnetism and plasma dynamics dictate the physical reality of the surface.
It's wild to think about.
That is just wild. The rover will be driving through a localized haze of hovering, statically charged glass. But that brings us to the visual mystery. Why does the white swirl exist? What is the prevailing scientific theory they are trying to prove with the Vertex mission?
The prevailing theory is that this local magnetic anomaly acts as a miniature, highly effective deflector shield against space weathering.
Space weather.
Space isn't empty. The sun is constantly emitting the solar wind, a raging stream of high-energy, charged protons and electrons blowing outward at millions of miles per hour.
I like to think of this magnetic field like a large rock sitting in the middle of a fast-moving river. The magnetic field is the rock, and the solar wind is the water.
That's a good visual.
The water hits the rock, parts, and flows entirely around it, leaving the riverbed directly behind the rock, completely dry and untouched.
That is an excellent analogy. To understand why that matters, you have to look at the water, the solar wind. Over millions of years, when these high-energy protons constantly smash into the unprotected lunar soil across the rest of the Moon, they cause a brutal chemical reaction.
What kind of reaction?
The protons break the chemical bonds in the iron silicate minerals of the lunar dirt. This causes microscopic blobs of pure nanophase iron to form on the surface of the dust grains.
And this nanophase iron drastically darkens the optical appearance of the dirt.
Exactly. The normal moon dirt basically gets a chemical sunburn and turns dark.
But at Reiner Gamma, the magnetic bubble catches those charged solar particles and aggressively deflects them away from the surface,
forcing them to crash into the surrounding plains instead.
The bright white swirl we see from Earth is essentially the original, pristine, unweathered color of the lunar dust. It is being protected by its invisible magnetic umbrella, while all the rock surrounding it has been burnt dark by the sun.
The magnetic field is literally painting a shadow of itself on the surface of the Moon by protecting the dirt beneath it.
It's a gorgeous mechanism. But this isn't just about solving a neat visual trick or proving a point about planetary geology, is it? There's a highly practical, survival-based application for this data.
Understanding this localized space weathering, and specifically how solar plasma interacts with magnetic fields at the surface level, is vital engineering data for human survival. If we are going to build long-term lunar habitats for Artemis astronauts, radiation shielding is the primary concern. We need to know exactly how solar radiation behaves, how dust gets electrostatically charged and clings to spacesuits, ruining their thermal properties.
If the Reiner Gamma anomaly proves that a relatively weak magnetic field can effectively deflect solar radiation, could we artificially replicate that?
That is a long-term speculation. Could we generate our own artificial magnetic shielding around a lunar base to protect human crews from solar flares, rather than forcing them to live under 10 feet of compressed regolith?
The data collected by Lunar Vertex informs the architecture of our future in deep space.
It does. It connects the deep science of plasma dynamics directly to deep space survival.
Well, we have covered an incredible, massive spectrum of engineering and physics today. Just to recap the sheer scale of what we've unpacked for you, we've talked about flying a nuclear-powered octocopter through Titan's dense, freezing methane atmosphere, hunting for the chemical origins of life in a cosmic crockpot. We've plunged through the sulfuric acid clouds of Venus, designing titanium spheres to survive a crushing supercritical pressure cooker just long enough to hunt for the noble gassed ghosts of a lost ocean.
Also amazing.
We've navigated the razor-sharp dust, the hypersonic exhaust plumes, and the terrifying cryogenic shadows of the lunar South Pole to prospect for rocket fuel.
Right.
We've mapped out the insanely complex robotic relay race required to launch a solid rocket motor full of dirt off the surface of Mars. And finally, we've explored surfing invisible magnetic force fields and levitating electrostatic dust at the Reiner Gamma lunar swirl.
It highlights a profound truth about exploration, I think. There is absolutely no one-size-fits-all approach to the cosmos.
None at all.
The engineering required merely to survive the first 5 minutes on these worlds is every bit as impressive and requires just as much fundamental innovation as the groundbreaking science those instruments will gather over the following years.
It is a testament to humanity's boundless curiosity and our incredibly stubborn capability to solve seemingly impossible physics puzzles. So I have to ask you, the listener, if you have the chance, knowing the mechanics and the terrors of each environment, which of these extreme worlds would you choose to land on?
It's a tough choice.
Would you strap on the cardboard wings and fly on Titan, or brave the blinding light and deep shadows of the lunar South Pole? Each one is a lethal frontier in its own right.
They really are.
And before we wrap up this deep dive, I want to leave you with one final provocative thought based on everything we've explored today.
Go for it.
We tend to look at these landers and probes as isolated tools, custom-built to study individual disconnected worlds. But step back and look at the sheer violent diversity of the environments we just analyzed. We have acid clouds that melt lead. We have freezing organic snow falling on water ice bedrock. We have shattered microscopic glass levitating in magnetic bubbles. We have craters sitting at absolute zero.
It's chaos.
If every single destination in our immediate celestial neighborhood requires a completely reinvented landing architecture just to survive the atmospheric physics, what does that tell us about the chaotic, violently divergent history of our solar system as a whole?
It's a great question.
When we send a probe to a new world, we aren't just crossing physical distance. We are colliding with entirely different, wildly divergent timelines of planetary evolution. It makes you realize that our safe, predictable suspension bridges and mild weather here on Earth are the ultimate anomaly.
We're the weird ones.
The extreme chaos is the norm. So how many more impossible, lethal environments are waiting for us to figure out there in the dark?
That is exactly the question that ensures we will never stop exploring.
Thanks for joining us for this deep dive. Keep looking up.